Hello, so with this recording, I'd like to introduce the topic of flavor symmetry. What do we mean by that? So when the neutron was discovered, it was noted that the mass of the neutron is very close to the mass of the proton. And so it seems like those two particles are somehow related, even though the electric charge is different. The proton is charged, the neutron is neutral. And you can see here that the masses are really very, very close, about 1 MeV or 1% different in mass. So Heisenberg proposed, and that was in the 1930s, to regard them as two states of the same particle. They were really so different that you could, think that they are basically the same, just, a rotation from one into the other. And that's exactly what he did, considering them as one particle, a nucleon, where the proton, is described as a duplet with, an up duplet, and the neutron as a down duplet, similar to an up quark and a down quark, an electron and a neutrino later on. Those particles were not known at the time. So he introduces a new concept, so-called isospin, or strong isospin, where he's doing exactly this. He labels the proton up and he labels the neutron down. So far we haven't done anything, but introduced new labels for particles, new particles at the time. But now if you assume that the strong force is invariant under rotations in this isospin space, meaning, when you flip the neutron into a proton and vice versa, those rotations are invariant, the strong force is invariant under those rotations. That means, or what follows directly, is that the isospin is conserved in all strong interactions. So that is what really the conclusion is of this introduction of those new labels, is that isospin is conserved under strong interactions. So this was proposed in the 1930s. Again, we noticed the symmetry in nature, and from that symmetry, a conservation law follows. Even so, and we can conclude, physics, cross-sections or ratios of cross-sections from it, without understanding, in this case, QCD with strong interaction. So this is very fascinating, and you can just apply this concept now to other particles. For example, the pion. The pion has an isospin of 1, and there are 3 pions, or 3 states. The 0 state, the up state, and the down state, which is the pi plus, the pi 0, and the pi minus. In general, you can conclude that the multiplicity of your particles, as you see the neutron, the proton, the pi plus, the pi 0, and the pi minus, the multiplicity is 2 times the isospin plus 1. Isospin equal 1 means that there are 3 particles as part of the representation. So far, so good. So later, this concept was, moved to other new particles. Many new particles were introduced and produced in the emergent accelerators and experiments on the market, and people try to classify them in those by their isospin. Gell-Mann and Nishiyama empirically observed that there's a relation which holds this equation here, which is that the charge, if you assign the maximum value I3, the third component of your isospin, to the member of the multiplet with the highest charge, in the previous example was either the proton or the pi plus, then the charge of this particle follows from the isospin, the baryon number, and the strangeness. We looked at baryon number and strangeness before. As a reminder, strangeness is the number of strange quarks in the baryon or the meson, and the baryon number is simply the number of baryons. So if you just look at this as, for example, for this pion case, we had the isospin equal 1, baryon number equal 0, strangeness equal 0, which follows that the maximum charge involved is 1, which is the charge of the positively charged pion. So far, so good. This was empirically observed, but once you then later discover and develop a quark model, this is then in the 1970s, you can deduce this equation directly from the assignment of isospin to quarks, which is rather fascinating. Again, we don't understand the physics fully, but just from the symmetry you can, and empirically, you can deduce information about physical systems. However, if you try to now extend this idea of isospin to the complete quark model, you find that the symmetry starts to be broken. It already starts to be broken slightly when you include strangeness or strange quarks, but it's badly broken when you include charm, bottom, or top. And the reason can be seen here. The up quark and the down quark, those are the particles making up ions and the neutron and the proton. And even if you include strangeness, the difference in mass is not very large. So, the symmetry, the particles, really look like they're the same particle in a different state of the same particle. While when you introduce other quarks, heavier quarks, charm and bottom, you find that the mass difference is so large that the symmetries are broken. So this concept starts failing because of the large mass differences, because the symmetry is broken. All right, so from here, we now go to discrete symmetries. And again, from the observation of those symmetries, you can deduce physics without fully understanding the underlying physics.